believe Bangalore plays a very important part in the future of RISC-V. In fact, the company I work for, Tenstorrent, we've invested heavily here. We have a large office. I think it's that way, right next door. And in that office, we have a very large part of our RISC-V development team. We're committed to India, we're committed to Bangalore, and we're not alone. Worldwide companies are coming here. Companies, founded in India are springing up with RISC-V technology. And we believe this is a tremendous opportunity to move forward, to grow. And my sincere hope, and our company's sincere hope, is that this event is one step forward towards the path, towards a great, strong, vibrant.
To build and own stuff here. And I shared my experience working at AMD and Intel where we had really great people, but sometimes the ownership was somewhere else or the management didn't understand how to work with the teams here and the stuff that we transformed a number of groups. And Jaya Jagadish, who worked with me, and Deepak, where we had a huge transformation at AMD. Unbelievably positive experience for me. Kind of inspirational.
Can I trade mics with you? People can't hear you.
Oh. So, does this work?
Push the button.
How about now? Is that?
So, you want to chaos?
How about now? Oh, wow. All right, now I'm really excited about this mic. This morning I wasn't looking forward to a mic that worked, but now I am. So what we talked about was how do we start some more companies, and then how do we do the transformation where the companies here can own IP and technology? And I'm going to give a talk about this, but one thing is you have to do something new, good news, transformation with AI, with RISC-V, with data centers. There are so many new things happening. It's a good time to do new things when new things are happening. And then Rajeev and I have been talking for the last year about how do we do something really big, but it doesn't start out sounding so big we couldn't do it. And the journey on that is how do we start multiple small things that work together to create something special. And then a transformative technology like RISC-V is open. Many people can do it. That creates the innovation. And so we had some inspirational conversations. We were in New Delhi a while back, reporting out, let's say, progress. And then we invited Rajeev here today to do an opening for a new startup that I'm going to talk about, and also see the offices and the progress we made. So I'm pretty excited about that. Do you want to come on the stage and?
Thank you. Yeah, okay. So the lights are on and the mic is working. So look, thank you, Jim, Raja, Jaya, Tanuja, and all of the nerds in the audience for inviting me to speak here. It's not usual part of my itinerary that I go to a nerds conference, but it's obviously a welcome break from what I'm doing now, and I will continue to do for the next 30 days, which is electioneering in Karnataka. Look, nerds talking to nerds about RISC-V. So my journey started as a nerd talking to nerds about x86. So certainly we've traveled a distance when we're talking about RISC-V. I am gagged by the model code of conduct, so I can't speak too much about the government and what the government's intentions and vision are. But I'll certainly share some thoughts with you about how I see it and how I believe this is very important. So first of all, congratulations to Tenstorrent. Congratulations to Bodhi Computing today, which got launched as a startup. My best wishes to the teams. I think we can certainly accept and agree, whether you are a full-blown nerd or a work-in-progress nerd or a has-been nerd, that we are living in fairly interesting times in the technology space. There are multiple asynchronous trends that are, in some cases, related to each other, linked to each other, some that are operating totally independently, but that are certainly shaping what the next 5 years of tech will be and what the 5 years of semiconductors and compute will look like. And I don't even speak about the next 10 years, I speak about the next 5 years. And I'm reasonably convinced that the next 5 years are going to be deeply disruptive. At different levels, at different places. And I see the internet changing, the compute side evolving and disrupting, the entire semiconductor space, the geopolitics of technology going through an almost irreversible alteration, and the centers of gravity of innovation and technology being, in a sense, reformed, rebuilt around newer and newer geographies and newer talent pools. And I think that is the opportunity for young Indians and young startups in India, which is to build and create these new ideas and new devices and new products and new solutions that are, in a sense, what the world is looking for, what the world is moving towards, and doing so in partnerships that are absolutely typified by and characterized by what Tenstorrent is doing today here, and has been done in the past by the AMDs and the Intels of the world, but at a different scale and with a different perspective. So I would just today, obviously, RISC-V is a very, very important part of this future journey of tech. I certainly believe that open source and the non-proprietary world of products, devices is manifesting itself, whether it's in wireless, whether it's in compute, whether it's in automotive, whether it is in the internet. So I think this is really the time and place for RISC-V. Certainly, this is the time and place for RISC-V in India. This is certainly a time and place for partnerships across geographies and across countries and across companies from the US, Europe, with startups in India to shape the future of RISC-V and therefore the overall technology space as I described it. I won't speak too much more today. I certainly don't want to come between you and the other nerds who will speak. That's not my intention, but I will say that I have spent about 30, 35 years in tech, and I've never been more excited about technology and more passionate about the future as it is going to happen. And I am deeply gratified that just 1 year since the first Semicon India conference in India, we have a collection of youngsters like you and startups and leaders from around the world coming together to discuss something as specialized and focused as RISC-V and the future of RISC-V. So I wish you all well. More power to you, more power to Jim and his team. And to quote another Star Warsian nerdish quote, may the force be with you and all the very best. Thank you.
Right. Whew. Well, welcome everybody. When we would look for space all around, Bangalore, and we saw some really interesting properties, but we saw this, it was really cool because there was lots of empty space at the time, and it had a conference center, and I thought, oh, we'll have a conference. And then you guys are the guinea pigs. Thanks. And well, and I've been to a bunch of tech conferences recently, and it feels like there's a lot of marketing stuff. And so I was joking with the team about, let's just have a nerds conference. And then they named it Nerds Talking to Nerds, which really cracked me up because I thought it should sound more serious or something, but no. So, and then I'd also like to welcome Matteo. Would you stand up and say hi? So we met a long time ago, but recently we met again. And he's a friend of Raj's, and he's leading the Supercomputer Center in the EU in Barcelona. And it's really interesting. We've been traveling around the world about talking to people about building high performance computing where the people building the computers want to own it and define what they can do. These guys are experts in HPC software. They have a very strong opinion of what they want. And the thing about open means you can then, up it's dark, a little lighter. You guys you're getting there, dialing it in. Dialing it in. That's better. I can see you. I don't know if you can see me. But that concept of being able to own it, drive it, change it, modify it. I'm going to talk about some technologies that enables that. But it's really been an interesting year to go talk about this. So let me jump in. So at Semicon, I gave a talk which was called India Leads the World in Chips. And I thought that they gave me the title. Like I had never given a talk where the conference invited me to talk about their thing. And I thought, India doesn't lead the world in chip design. They don't. But then I realized, well, that's a problem statement, not a definition. Like, what would you have to do that, right? And then I talked to Rajeev, the minister, Ashwini, super smart guys, very technical, not your typical government guys who don't know what they're managing. So that was a really interesting conversation. And Raj and I have been talking ever since about what could we do concrete and useful to make things happen. And I took this as a challenge. And as I mentioned before, I like working with people here. I don't like the jet lag. But we're going to make faster rockets. It'll be easier soon. So we'll see what happens. And then the Tenstorrent, we started an office here and started hiring people. We're at 35 people. This team is great. They're doing. I got it here. It's great to learn from people, to work on derivative product. It's a great experience, but everybody in their life has to work on new things. My team building this, like, Karen, you want to stand up? Like, we started with nothing. And, he's an engineering leader and a manager, but also we had to figure out, like, where do we put the chairs and where's the cafeteria? How big is the bathroom door? It's a lot of work to do everything, and it stretches your mind, and it's really exciting. So here's a slide. We have a strategy slide, right? We're doing AI. We're doing RISC-V. We started it. Some years ago, Amazon showed this with Graviton, where they can own their security processor but have commodity CPUs or AI. And that means you can do a really complex product but have having to own 100 IPs and have 1,000 people. You can buy some pieces and you can build some pieces. It lowers the barrier to technology. It's really interesting. And I'll show you a picture. And then part of our strategy is India. There's great local talent here, right? And we really believe in open source. Open source is a one-way door. Once you go from commodity to open source, nobody ever goes back. That's what happened with Linux. That happens so many of the tools. AI is fundamentally, well, AI is an interesting one. Most of the models in research are very open. Some of the work is becoming proprietary because of the cost. We're trying to address that. More people are doing new designs on RISC-V than any other architecture. And what I mean is Intel and AMD, that's two. ARM is ARM, Apple, Qualcomm, like Google, Microsoft stopped, Google's still going. I forgot the other one. There's over 20 companies building new RISC-V processors at all different levels, right? And the ability to do that means that's where the innovation is going to happen. And we not only are building RISC-V, we use RISC-V in different parts of the stack because we could. We could not do that with ARM or with Intel or somebody like that. You can do what you want, you can innovate, and that's a game changer. And there's just a couple people apparently signed up to be part of RISC-V. It's kind of amazing, including the big players. And we're seeing like big companies that are ARM places are using RISC-V as microcontrollers, embedded processors. And this is an eat the world from the bottom strategy, but we're also going to work on eating the world from the top. So we build an AI processor. AI processor software is really hard. We're struggling, by the way. We're a year late, but we're getting there. And then we decided to put RISC-V processors in our next chip, which we're taping out in about 2 months. And everybody said, well, where are you getting the software? And RISC-V runs Linux and all the open source stuff, but you have to port it, you have to qualify it, you have to validate it. And we started to see the ball really start to move last year, which is pretty exciting. And then the progress is accelerating, right? KVM works. We just had a demo, and I'll talk about this in a minute. I have a picture. We have an emulator model. It has a virtualization layer. We booted Linux. We booted real applications on it in the emulation. Some of the pieces work great. Some of them don't work great, but we have the whole stack and environment progress accelerating. There's now a big effort to do an Android port. Google is in, Facebook is in, big players, and a whole bunch of small people. The RISC-V is moving. And then to drive this a little bit, we added some people to our team. Olaf Johansson worked with me at Apple PA Semi and at Tesla. He built a Linux platform that drives the cars. He's a great engineer. For a couple years, he owned Linux for ARM. He also worked on Chromebook. He's a great guy. He knows everybody. And then I'd like to share that Raja Gadori has joined our board. Stand up, Raja. And then a friend was pitching me, he said, hey, do you need a CTO? I said, no, I just got a board member, combo CTO, AI strategist. He's a pretty good deal. Raj and I, we figure we've worked together for 15 years right now. We're kind of like brothers with different parents or something. Sometimes it goes really well. Sometimes we have fist fights. But really appreciate you joining and helping and driving this. Right. The second thing I'd like to announce is, Sambit, where's Sambit? You want to stand up, Raghu? One of the things Rajeev asked us to do is he wants India-founded, owned, operated companies. And Tenstorrent is a Canadian company with an Indian and an American subsidiary, right? So I was talking with Sambit, and Intel was stupid enough to let him go. And we worked together at Intel, where he's a real product guy and builds stuff. And Raghu, where are you? Oh, is he running? He's probably working. Oh, there he is. I was going to say he's our VP of software. So this is a joint venture. It's an Indian company. Sambit is CTO. CEO, Raghu is VP of software. They got going. We have a stake in the company. We also have a stake in their future. Raghu and Olaf have already been coordinating a whole bunch of RISC-V divide and conquer software porting work. And yesterday they did a demo for me, which included that emulation, virtualization, Linux, and application layer booting. And this is the picture of the team showing on the one screen is it booting up, and the other one they're describing to me in some detail all the nerd bits about all the layers and how that all fits together. So these guys have a boatload of experience. We're on quite a path here. It's really, really interesting. And then, let me just go back. And then Raja and I, we also are involved with 4 more stealth startups. Some will be Indian companies, some will not be. And our picture is, you need to build advanced technology. You need a CPU, you need AI, you need a fabric, you need a server, you need a data center, you need a GPU. And if I only knew somebody who could build a GPU, like, we'll see if we can talk somebody into building the GPU for us. What's that? I mean, well, we're, you need the experience, but you also, it's a lot of people and a lot of pieces. We need support. We're talking with people in the EU. They want to own stuff and build stuff. They have value. We're talking with Japanese supercomputer people. They want to own it. They want to add value. It's really interesting. But to build the big products, you need all the pieces available, somewhat coordinated. And the concept Raj and I have been talking to investors about is each company is solid, standalone, has customers, it's independently viable, but together with a little bit of collaboration, it's bigger than the sum of the parts. That's starting to happen. I just want to talk about RISC-V for a minute. So when we started this, I thought, oh, we're building a new processor from scratch. We're going to have to build a reference model, test generators, all that. The open source world on RISC-V is better than most companies' internal development stuff. There's multiple reference models, multiple test generators, all kinds of test collateral. Tenstorrent, among other people, like there's a RISC-V International, they support this stuff. Ventana, I have friends at Ventana, Revos, Sci-Fi. They build internal stuff, but they upstream a whole bunch of stuff, and it's good. And the cool thing about open source is the best stuff makes lots of progress and people want to participate, and you can get a magnification of your efforts. So the RISC-V environment is getting really good. We want to do the same thing for AI, for GPUs, for fabrics, for servers, for chiplets, so that you can really build products. So, and that's why I want people to kind of come here and listen and talk, and I want to listen and figure out like what the next steps are. Some of this. I have 2 slides about how we build our AI engine. So this is really cool. So this is a picture of a Tenstorrent, what we call Tensic processor. It's actually 5 small RISC-V CPUs attached to a very large multiplier array and vector unit array. And when you write a program, you often think about, I load some data, I do a multiply and add some operations, store some data. So we write programs like that, but we have a cross compiler, which then takes that program and separates it into pieces. So imagine CPU 1 is reading data in. We took the one program that looked like a serial program and made it into 5 independent programs. So one is sourcing data, one is formatting data, one is driving the multiply add units, one is reformatting data if necessary, doing control flow, and then sending it on its way. So at one level, it's a cluster of RISC-V processors. At another level, it's an out-of-order execution machine driven by software, the whole RISC-V tool chain, the whole AI tool chain, running independently. And then to make a chip, we take an array of those guys and get very dense computation. So locally, it's a programmable engine, but globally, these chips, processors can all talk to each other and collaborate together. You can have cores in one place, send data to another place. This is a challenging software stack, but the components are straightforward and we're making progress on this. So we wrote 2 software stacks. One we call Buddha, which is for people who want to write high-level PyTorch TensorFlow programs and have a compiler automatically compile through the stack. So you take the high-level program, you make a graph, you lower the graph, what they call shard the graph across arrays of processors. You insert buffers, you do all this stuff, and it's automatic. And we demoed for a large cloud company compiling a PyTorch version of ChatGPT, something or other, to 32 chips automatically with a compiler. They said nobody had ever done that before. So this is cool, but it's challenging to get the performance. It was faster than an NVIDIA box, slower per chip, but much more cost effective. Pretty soon we're going to introduce a second software stack, and this is actually how AI software today works on NVIDIA. At the low level, there's an assembly language called PTX, and then there's CUDA, and then there's libraries, and a number of frameworks to translate PyTorch to the low level bits. That was typically called something like Metal. So Apple has Metal. It's, you know, program on the bare metal. So we're going to actually run both pieces of software. So if you want PyTorch to compile, that goes through the PyBuddha stack. And if you want to be a bare metal programmer compiling from C++ and have control at the low level, that'll be our bare metal stack. And we're going to open source both of those this year. I hope in Q2 we get at least one of them open source, and Q3 the other one. Since Rajeev joined us, I'm going to invite him to kind of walk through it. I'm expecting some course corrections, but I think we'll do pretty well. So for our next generation chip, it's a great RISC-V processor. We also downloaded Berkeley's open source, the Rocket and Boom Core. We've used those in our internal testing environment. We've upstreamed a vector unit. Our RISC-V team built a vector unit, bolted it on the Boom Core, and upstreamed that. We've made contributions to the open source world, but we're building a big, crazy, out of order, 8-way issue, maximum performance processor. And we started benchmarking it. We were a little surprised. We expected a pretty big gap between like AMD, Intel, high-end ARMs and us, but the RISC-V compiler world is built on the same GCC and LLVM optimizing compilers, and the initial numbers look really good. So we have very good performance modeling. And then when we showed people this as part of our AI strategy, they said, hey, we're interested in this as a CPU strategy. And people who want to own their own compute, supercomputer guys, big hyperscalers, they're interested in this as a technology. And then almost everybody asks us for a variation. And the team's very excited about this, / stressed, because you really want to build one configuration, but people want different sizes, different performance, optionality on vector units. So we're building this as much as possible. It's a configurable core. So if we license a core, you can kind of dial in the PPA targets that you want. And then here's a picture. We built both cards. That's a wormhole card, which is our second generation part. And that box right there in the bottom has 32 AI processors. Each one has native Ethernet. So we can stuff 32 processors in a box for 6 kilowatts compared to 8. And then we can hook them up natively with Ethernet, so there's no extra cost to that. So that's the product we're building. So this is a little bit of an artist's conception, but let me explain how the chiplet world works, right? This is an array, oops, memory controller. We've talked to a bunch of people. There's people doing different things. DDR controller, HBM, large cache controller. The same with networking. There's low-end Ethernet PCI Express, but there's really high-end DPU processors. So Tanuja and I, we've talked to like 10 or 15 companies building components. So here's the cool thing if you're a startup. You want to innovate on a memory system? Somebody might want to buy that. You want to innovate on AI? Somebody could buy that. You want to build a server with very large memory? Maybe it's all DDR. You're a supercomputer company? Maybe it's all HBM, right? This gives you optionality and lowers the bar. It's a really interesting change. And it's driven by a couple things. The die-to-die PHYs are a reasonable cost, so you can put multiple die in a package, assemble that, and ship it reasonably. I've worked on really expensive packages before. You know, we want to solve this problem inside the environment of reasonably cost components for every single piece, so we can take this to market in a lot of different ways. So Tenstorrent, we build AI products, but we realize we're a design company. We're designing CPUs in AI. The delivery method is sort of up to what the customer wants. There's IP, there's a chiplet, there's a package part, there's like a board. So we'll see how that goes. It's really interesting. And AI people, they want everything. There's all the young guys don't even know you can buy computers. Everything's on the cloud, right? And that's actually a good way to do some things. Some people want to own their servers. Some people want to own the IP technology. And we need to be flexible. And the cool thing about RISC-V is nobody can tell me what to do. So if somebody wants to license it and it's a good deal, we could do that. I'm not restricted by an ARM license or anything. And yeah, I think this is going to be really interesting. For the next couple of years, it's going to be really hard because making things interoperate and be compatible when everybody's trying to do their own special thing will take a little while, but we're going to pull it off. Okay, so here's the summary slide. Again, I want to thank everybody for coming. So we're building some really great teams in India. I think Bodhi's going to be the start of something really great. And Raj and I are working on a couple more adventures we think is also going to be great. RISC-V is part of the plan, and it's a key part because that's where we can change stuff. Right, this is a really big deal. And that is going to enable a whole bunch of really interesting designs. 100 companies innovating is going to be way faster than 5. So, who wants to build something new? Thanks, everybody. Sure.
Jim, what process node you're talking about for HPC?
So our first 2 chips were in GlobalFoundries 12. The one we're about to tape out is 6 nanometer. When we go to chiplets, it's mostly going to be 4 and 3. And we're talking though with all the obvious foundries about what's most cost effective. And the interesting thing is the roadmap for the die-to-die PHYs and the package. So we have lots of opinions and we're working through that technology stuff. But the foundries are really interested in this because it opens up a whole bunch of new markets. And some of the chiplets, you can do your prototypes now on a shuttle wafer, so it really changes the cost structure for a startup, which is really, really cool. You go build a big AI chip, 4 nanometers, this is 15, 20 million bucks. You go build it on a shuttle for your first tape outs, it's way different cost. So the thing I'm thinking about is if lots of people figure out how to do chiplets, that we might want to, and the reason I'm talking about this, it would be really exciting, we could do a group tape out that looks like a chiplet shuttle. And this is where some government assistance would really be helpful to drive technology and lower costs for startups. Yeah.
Yeah, hi Jim. So the question I was trying to understand, compared to the ARM processor versus RISC-V, in terms of raw performance, maybe ARM could be slightly better, but in some workload, which kind of workload do you see that RISC-V will be much better technology?
Yeah, so the question is, wouldn't ARM be a little bit better? So ARM has had more time to optimize, but they're also on their high end, they're aiming at a very particular target. So for our AI workloads, we needed some new data types. We needed a very different cache size ratio. So for what we're building, we think we're better configured. So we have an advantage. The gap on compiler was pretty small. We need to do some work on the vectorizing compiler. But then when you're building a solution, not just a processor, not just a benchmark, you're optimizing PPA and how everything works together. The cool thing about RISC-V is if you want an accelerator port or a wider bus, you can go do that, right? And that's a big change. Like we're building very large L1 and a shared last level cache. It's a much simpler structure than the 3-level cache and some of the other guys' stuff, but it's better for high performance computing. So I think it's the optimization that matters. At the instruction set level, it doesn't matter that much. But if somebody doesn't have the data type you want and says, I won't give it to you for 3 years, the whole time you're worse off. We do 4, 8, 16, 32-bit float. We do standard float, block float. We have integer float conversions. We build all that stuff just the way we want it. It's really fast.
Thank you.
And that's why RISC-V is going to win.
Hey, Jim, good morning. So there was time when there were a lot of players trying to put ARM-based high-performance compute in data centers, right? And gradually, I think the number of players came down. The penetration of ARM-based compute, I feel, did not go as much as it was expected some time back.
Yeah, I have some opinions about that.
And you know,
don't tell anybody what I think, by the way. Just keep it in here.
So what are the things that that you believe that RISC-V has a way to go towards high performance compute, and what could be the reasons that we didn't have that much success with ARM, but you see that happening with RISC-V?
Yeah, so here's the thing. So processors come in small, medium, and large sizes, right? And ARM's DNA was small, right? If you go to the big core guys at Intel, their DNA is big, really big. I'd say AMD is more of a just right kind of size. It's nice, yeah, there, right? But so a couple things happen. Some people naively thought it's ARM, it'll be easy to build. High performance processors are really hard to build, right? And the other is, for certain kinds of changes, ARM is the bottleneck. I worked at Apple. I had some requests. They told me no. They wanted to be the one to lead with certain technologies because they own the architecture license. They also had a belief, and maybe correctly, that keeping tight control of the architecture meant everybody's on the same software stack, but that limited innovation, right? So on RISC-V, some of the people building this are small and medium processor guys. I'm a big processor guy, right? So, and some of the team, they built really fast processors. So we know how to do this stuff. The other is, if somebody came to me and said, Jim, I want to build my own high performance computer, I can license them the whole stack, right? The reference model, the performance model, the validation infrastructure, the first generation. Like nobody else is going to do that. If you go to Apple and say, I want to license your processor to build HPC, there's no way, right? So I think people could start building high performance computers with RISC-V with a better starting point. The Berkeley cores, if you're doing medium computing, they're great. They're great. Students built them. They're fantastic. 2 issue, 3 issue. They're not 8 issue. They're not the world's best branch predictor and prefetcher and stuff. But talk to me. I'm a sales guy. I could do business so you could get a leg up, right? And the reason I'm confident that that's a good business deal for me is I can make money selling that whole infrastructure, and we're already thinking about our next thing, which is another big step up, right? So it's a different game. It's a great question.
Hi, Jim.
One more? Oh.
Yeah, I just want to know what you think are the software challenges on the compiler front. So do you see optimizing compilers or auto-tuning as the future for like replacing CUDA or those kind of languages?
Yeah, so your question is the challenges on, so there's a couple, the challenges on the compiler front, there's a couple pieces. So the basic optimization layers in GCC and LVM are pretty good already. And the ARM and RISC-V backend targets are similar enough, that's working, right? And then people are getting very energized about putting some work into this. The next piece is what comes next, right? So my belief, has anybody heard of ChatGPT? Maybe? Oh, it's everybody. So that's helping people write Python and C programs and stuff. Pretty soon we're going to start to write binaries and multi-threaded programs, right? One of the reasons we're building this technology in an AI company is AI is going to write models and programs at a deep level, which is going to transform how compilers, software stacks are built, right? And then the people who move the fastest to go build the next generation hardware are going to win. And this is a really hard problem, and it's unknown territory. This is a belief I have. Like Raj and I have talked a lot about how, like, and we've seen this transformation happen in GPUs. They started running really simple shader programs. They've become fairly sophisticated. as a as a processor, they're still pretty simple engines with sophistication in software, which is challenging. CUDA is very challenging. So the thing that the intellectual project is, how do we leverage AI writing code to build new kinds of technology? And then what does that mean if you're like a compiler person? We don't know yet, but the changes are going to come pretty fast. And we think there's going to be a combination of CPU, GPU, and AI. Okay.
Hi, Jim. Hello.
One more. No, we're going to be out of here.
Yeah. One question specifically on the.
I think their helicopters are here. Okay.
Yeah. My question is more pertaining to the edge processors, similar to Cortex-M kind of thing in RISC-V. So, and it's very similar to the question that was asked earlier. So, what you see is, a lot of out-of-order processors and, see innovation in the architecture side. And you see innovation in DL compiler, right? Deep learning compilers. So, what you see would dominate, the architectures or the compilers going forward, especially for, in HPC, and I know there might be something else, but I work on edge, so I just want to focus.
Yeah, so nothing's going to dominate. Like, this is the thing. The diversity of applications is so high. And I think ARM did a great job because they had the M class to R class, multiple sizes of processors. Like a lot of companies, everybody, they start out with a high, medium, and low, and then everybody kind of gravitates towards the middle. They've done a good job at differentiating the pieces. The thing they don't do is they control the processor, which means if you're trying to build something specific, like the RISC-V processors we use in AI are heavily optimized for our use case. We added semaphores, we added data types, we added a fast accelerator port in and out of the floating point units. So we did a whole bunch of modifications. So the pipeline was conventional, but its interface to the local computation and data movement was very customized. So RISC-V lets you do that. So there's going to be multiple open source processors. When you're building something new, you're going to look at what's available, look at what you might buy, look what you could build, and then look at what changes you need to make it work in your system the best way. And the same thing is going to happen on the software. Like, you'll take an open source compiler, but you're going to put into it a whole bunch of stuff so you can drive, say, your own data DMA engine or your own encryption instructions. So the range of compute is really broad. There's no domination.
So there is no one solution. It has to be a
one
holistic
solution.
one.
This is why having lots of different people do different things. Let's just go explore the territory.
Okay, thank you.
Okay. All right, thank you very much, everybody, for your.
Great questions. Whoa, that's loud. Great questions, everybody. It's wonderful to have you all here. So what we're going to do right now is we have breakfast and snacks and drinks set up downstairs. We're going to take a 30-minute break, and we're going to reconvene here at 10:30. So use this time to network, to get a snack, and we'll see you soon.
So if you haven't, please go and have something. We'll start in 10 minutes. Thank you. Hello.
So we're ahead of schedule.
Hi. Yes, I have. It was in a PDF. Do you have a PPT? I don't. Yeah, I've got the PDF.
And for some reason,
Can I share the link for the camera?
Uh, Not sure if Canva would be. There might be some link. We have the PDF. We can do the PDF. That's fine. Yeah.
He was asking PPT, so
did you make an announcement?
Not yet.
Same. Okay. And,
Hey everyone, we're going to start in 5 minutes, so please take your seats.
That's microphone.
You want me to up the like put the Raghu's bio up?
Yeah, get his presentation up, and then I'll start.
Hello.
Raghu?
We're gonna get your presentation up, and then we'll be ready to go. Hi, everyone. I hope you all had a good snack. Is it? We, sorry, fixing my collar here. I'll fix it later. So I'm very pleased to be able to continue the news about Bodhi computing today. And I'd like to introduce Raghu Bharathalawar. And Rathini, would you please come up to the stage? And they're going to give a presentation, and we'll have some time for Q&A after.
Hey, thank you, Bob, and good morning, everybody. It's really nice pleasure to connect with you all on the socials, events, and ARM. That really pumps me, and now I'm thinking whether to go through the slides or whatever the dialogue we already talked, how to reinstate. But again, thank you for this opportunity. A little bit about Bodhi. So we just came together late last year, I would say. There's a big vision Jim put us in front, how we can build a RISC-based server systems and propelled for India market. So that motivation of, for India and an open ecosystem and open hardware, that really moved us. Between me and Sambit, we came together how to get this going and be part of this ecosystem. We are not going to own this. We are going to be working with you all, connect with you all, drive with you all, and make it happen. Okay, since it is going to be a complex problem, complex challenge, but that's where the opportunity lies. And we are very excited, maybe a small puzzle solver, we are be part of this community to bring this going. And with you all, we are going to make it happen. So that's the background of Bodhi. And today is our day that we are starting officially with all the inauguration. Thanks to Tenstorrent team, Jim, Tanuja, Shrikant, all of you making it happen. And thank you again. Okay. So the topic that we wanted to pick up, obviously my background is software as an engineer. So that's the topic I picked, to bring you all, with the knowledge what I have and my team have gained, with 20 plus experience, both in 86 and ARM world. We got an opportunity to work on in various big companies. And with that experience, we are entering the door through of software. That's our contribution, from our end of Bodhi, right, to the community. So the topic is, what is service system and service software? In RISC-V, what do we see? And instead of quoting as a challenges, I call it as an opportunity, because this is where we all as a nerds can come together to solve it. So we are going to be together in this journey to do it. So today's agenda, I have got 40 minutes. So it's a topic itself, we can go for 2 days. So I will try to cover it in 40 minutes when we'll have a Q&A for that. So we are bucketed into what is service system, how we are targeting, what are the market segments associated, what are the common system requirement when we call it as a system, and what is common across all these segments. And then what are the ingredients and software stack from our view, what do we see based on our experience and how we think we can come together. And then the community, which is the most important part, the industry momentum so far, and then the software ecosystem from our eyes. And obviously we are open for more conversation as we go through. And we've been working for last 4 months. We try to zoom in our understanding of RISC ecosystem. And then what are the different software layers in each of the layer, all the way from the SBL boot to the firmware, to the drivers, to the kernel, to the OS, to the middleware, to the libraries, to the SDKs, to the references, and the real application, how it is going to work. So we quickly, for last 4 months in RISC, we assembled our understanding, and we would like to share this with you openly. So we will share that as well. And then eventually, what is the conclusion and what is our big ask for you all and for us, how we can connect together. So that's what we are going to cover. If anything not covered, feel free to open it for a Q&A and we'll try to cover it. Yeah. So with, so service segments, when we say is, so the revolution of technologies has opened up many use cases and many segments in this server, right? If we start from AI, today's AI penetration, the neural network processor is only 1% of our brain. So there's a lot to be done in that, right? And then the data, if I look at the big data, the 3 years, next 3 years of the data going to be generated is equivalent to last 3 years, including today, last 3 years of data. So that much data propagation is going to happen. That's what we call it as a big data. And then in the networking world with the 5G, it just entered 10 to 15% of the world. It has not even penetrated to the 80% or 90%, which is that 4G evolution is going to catch up in 5G. And then obviously all the use cases in the media and the entertainment and everywhere we see more and more the data propellant is going to happen. So if I sum it up short, 20, 30 years back, how do we saw server was more of a socket opening? How do I do a data transfer with the client server model versus a distributed services in the server? How this distributed services in the ecosystem is going to work, whether it mean the near edge or far edge on the data center or in the data cloud. So this technology, obviously the nerds behind all this technology is making it more exciting and more to happen, right? So these are all the segments, that's what we are going to cover behind this. So with me, Ratina, who is our software architect, will be joining me, to cover this more in detail. So with that, we'll start with the system requirements. Yeah.
Thanks, Raghu. So we will start with the key requirements, system requirements. So you must be knowing that a server should be running 24/7 with no downtime for 7 days. The complete 7 years lifetime is the guarantee which we need to give for a server. So recently the server are increasing the VA bits. Basically VA bits meaning it is going to give the higher larger address space. Larger address space will enable you to run more and more applications, more VMs, and these things will enable sharing the server to a huge extent. The higher number of PCI lanes, recently so many accelerators and so many things are evolving, so we will plug in so many cards to the servers. So we need higher number of PCI lanes with low latency and high bandwidth. So the memory channels need to be increased because you need a lot of memory to process the data which is being generated. The Ethernet speed has to be increased. We need more Ethernet ports. The bandwidth has to be increased. The SATA ports, because you are generating a lot of data, you need a lot of storage actually. So this is the important requirements of the server. The accelerators, whichever things are plugged into the PCI cards, are being moved into SoC as well, because to improve the performance and power. So these things are integrated into the SoC, like crypto compression, all those things. So we expand the server into multi-socket instead of, replicating as a two different servers. Multi-socket will improve the power and performance actually. The RAS, which will improve the reliability, and we need a remote manageability to access the server, control the, you need to remotely update the server, debug the server, all those things are important. So these things are all the system requirements for the server. So you must be already knowing that the RISC-V has solved the problem, the microcontroller world, now entering into the AI/ML world. So for the server, these things are, several areas are open. We need to collaborate together to solve all these problems.
Yeah, just to connect back what Ratina is trying to cover here as a system requirement, to connect back to what I covered as multiple server segments. We see common requirements for each of the segments, even though each segment will drive its own system, solution for that. And each, of this market might need its own IP, right? When I say AML server, we need an AI accelerator or a graphics accelerator part of it. When we say a network server, we might need a additional, PCIe or networking accelerator for that. Similarly, if we go for a storage, we might need an additional SATA and coverage of that storage. So these is primarily to cover what are the key system requirements for across the board. And then, the particular segment specific server will drive its own requirements, which is vertically cutting across all technologies particular of that particular server. So this is what our views of what are the key requirements when we design a server, and how the software has to take care of it, because we cannot decouple the hardware requirements from the software, which is one of the biggest learning we had in the last few years in our experience, that the software has to be ready with those system requirements. To be honest, in the other way, software has to define the requirements of what is the partition of the hardware and software. And this is what we are approaching, and it is the right time as we are entering into this ecosystem with RISC already started solving in the edge devices or the node devices, and the low compute devices already been penetrated, this is the right time. With all the partnership, we are trying to define the spec of the partition of the server, how it is going to happen. Yeah.
So we will look into the server components, key components. Basically, this is the common platform components, so which is like a building block for a server in a layered form. So you have a CPU virtualization and the fundamental blocks like PCI lanes, whatever we discussed before, and the clocks and the fundamental IPs. So then we have the vertical component. Next. The vertical components, yeah. So this is system level components which cut across, basically like the BMC, power management. Power management handles the runtime power management, like active, idle, all those things need to be handled. The RAS, which is the reliability factor, need to be handled, cut across the system. The security and trace and debug. These are all factors which is cutting across all the layers. So then comes the network, the market segment specific thing, like AI segment has its own components. Then you have then you have a network segment which has a 5G, L2, L3 accelerators, QoS, crypto type of things, which is specific to the network segment. Then the storage segment has the RAID and other things, whatever needed for that. This is how we have put a few components here. It's not the complete. So we'll move to the next slide where we will see the segment specific ingredients. For a cloud storage, for example, this is the fundamental building block. You can see the RISC-V emulator is here. So or when you have a hardware, this will be replaced by the hardware. So which is based on, you are running the U-boot or UFI kind of bootloader, open bootloader. On top, you have a storage specific stack in the Linux, basically SATA, NVMe, all those things are there. Then you can optionally run the KVM or Docker Kubernetes for virtualizing or cloud, to enable it in a cloud. So then you have a OS, like you have different flavors, Ubuntu, Red Hat type of things. Then comes the storage specific things like SEP, MySQL, MongoDB, MinIO kind of components, which is cloud storage specific things. So when you come to the web service, these components a little bit change. Like for example, you have the same RISC-V hardware or emulator, and you are running on the same bootloaders, but the Linux driver stack might look little different. You have a crypto TLS is there, the high-speed Ethernet is there. On top, the OS is same. Then you get the different type of applications on top. Basically, the WordPress, Nginx is running the WordPress. Then MySQL is same. OpenSSL is there. Apache could be there. PHP could be there. And then Dovecot and mail server kind of things, CDN, all those things are there. These are web service specific things. Then you have a networking workload where you have pretty much same fundamental blocks, but the higher level stack looks a little different. You have open switch and then software defined network, DPDK, all those network specific things which can run the vRAN type of use cases, all those things can be there. So basically the thing is you have a lot of things common in the fundamental blocks, and the application specific or the domain specific things are coming on top in a different way. So how we want to build the software is, so we should have a common stack in the bottom, basically the common software stack. On top, we should have a domain-specific content, which is having the domain-specific modules or applications which is running on top. So basically, you have, I mean, everyone in the community can pick every area, domain, and they can contribute for this evolvement together. So basically, this is the ask here.
Yeah, I would like to stress the approach, right? You know, pretty much as we entered this phase along with Tenstorrent, right? You know, pretty strong team on the core side and the AI side. So this is where we got an opportunity to have a co-working model with Tenstorrent, which we believe we will extend to everybody, and we will come together. Which is in the current space, we saw the emulator is the way to start, right? So we are starting with the QMO, right? That's what the lowest path, and we are also working on a path where there is an FPGA we can quickly assemble. And each layer, as you see, we are trying to commonalize this common software. That's our proposal from all the segments. And obviously each segment will drive each portion is going to be driving each of these boxes, right? Typically it's a boxes, but an architecture, it's going to be a little bit more complex with interfaces and how what is my contract between the hardware and software. Those contracts, when I say contract, obviously it should be open contract, not as a closed contract between Tenstorrent and us. It's going to be for all of us. So that's where we believe we are all going to come together to establish those contracts, right? Which is easy enough for all of us to contribute and work together and deliver. And this is the common software, which is pretty much, you can see, hardware associated software or a silicon software or a platform software. So this is where that hard established contracts, we have to establish and make progress. And today, as Ratina is going to cover in few more slides, we believe QMO is ready enough. Obviously, the speed is not that much as you go for a hardware-based emulation, but we believe QMO is good enough to get started. Obviously, we are also contributing to QMO as we see some segments support is not yet there in QMO, which will be adding it. And we all can add, and then and those ingredients get going, and this entire stack can be built upon. And that you can see in the next slides, how we are built in one segment of the market with a couple of use cases we are able to assemble. And we obviously there are challenges which were opportunities we are able to resolve, and we want to open source it and get going on that. Yeah.
So now we will move into community. So basically how the RISC-V community has evolved over the period of time. So basically in 2010, the RISC-V started with ISA definition. So basically the software role was mainly to write some test code to verify the ISA. Basically it was more like a test software, which was happening for the last, 6 years at that time. So from there, from 2017 onwards, the POC SOCs, basically proof of concept kind of SOCs were started. Basically, it's a small processors used to solve the domain-specific problems like power management or communication controller kind of things. So basically, the software role was mainly like a bare metal software. Basically, it controlled the controller directly and solved only the domain-specific problem, and it was successful at that time. So basically, that was the time. So basically, that was happening in a closed development kind of thing. So then it moved on like 1920 time frame. The IoTG use cases, the end use cases, from the domain it moved to the end use cases kind of thing. The microcontroller type of processor also evolved. So that was used together in IoTG applications. So the software also evolved from bare metal to RTOS based firmware type of development. So the development tools also evolved, like the GCC type of compiler. So many things are become mature. So everything is readily usable for the application development or driver development kind of things. So even there, the development was more like a silo development. Every company was solving their own problem kind of things themselves. So in the 21-22 time frame, the complex applications like AI and all those things started. ASOCs, application process, that drive the need for Linux and stuff. Basically Linux and Linux-based drivers, AI compilers, and Android also started actually. So these things are coming up in these days. So kind of thing. So 2022 onwards, the high-end applications are dominating. Basically, the performance applications like HPC, automotive workloads type of things are demanding more and more need, and that is becoming like a server-grade SOCs. At the same time, the universities also accepted the RISC-V, so they are also having the courses in the RISC-V software, hardware type of things. The people, I mean, students are also. So at the same time, the RISC-V, over this period of time, it has fragmented into multiple extensions. So I mean, it's not a fragment. That's by nature, it is adding more and more extensions. So the community started standardizing them as a profile. So basically, for every use case, they have profiles. And then they are defining the platform specs as a standard specification so that we can build something based on a standard actually, so that it can scale fast. So basically the recent experience from the ARM V8 things are helping the maturity going faster these days. This is just a snapshot, quick snapshot of all the I wouldn't say all the open source, a snapshot of some of the open source key components grouped by the project area. So you can see many things are supported, some are in progress kind of thing. The complete list is here. So we can pick anything. I mean, whoever want to contribute, they can contribute. We can collaborate using this ecosystem.
I think, during this break, risk and server, particularly obviously on software, given the, our customer experience in the previous job I had was all about software. Now the hardware is becoming easy to do, or, and hardware is becoming the tough nut to crack. And, that was a question about. And the previous slide was to give a little bit of confidence how the way we are going to approach is how the ecosystem together we are going to solve compared to how 86 tried to solve its own, or ARM with a limited ecosystem, how they come together. And here, the confidence that we have with the given limited experience, we believe in all the layers we touched, and we are able to see that really the ecosystem is building up. And 2022 plus is what now I think we can properly make it more faster. That was the message with this had in RISC, but obviously our experience in 86 ARM, with that we can propel it even more stronger. Yeah.
So this is a typical website. Everybody must be knowing this. So basically, you will have Apache or Nginx or OpenSBI. You put together with OpenSBI, or you have a EDK2 based UEFI. So these two can be the bootloader. On top, you have a Linux kernel plus Ubuntu services. So here we have this stack like domain-specific stack like Nginx, MySQL, PHP. On top, we have a WordPress. This is how the software stack at high level will look like. So here, so we had to build everything from the scratch, like the OpenSBI, U-boot, Linux kernel to make these things work. So this is the thing we did. The same thing with the virtualization enabled, it will look little different. So you have a KVM module added to the Linux kernel. The KVM is the module which handles hypervisor extension in the RISC-V. So basically, the QMO which is running on top in the green box is different from the QMO which is running on the bottom box. The QMO in the bottom box is running in the emulator mode, which is emulating the RISC-V instructions on the x86 PC. But at the same time, the QMO on the top is going to run, use the hypervisor extension of this emulated RISC-V and going to run in the directly it is going to run as a native thing. Basically, virtualized extension is there. The libvirt daemon is the one which is going to control the QMO from the VM dashboard. The left side box, you see natively a MySQL, Nginx, PHP is there. On top, you have a VM dashboard, which is the control dashboard for controlling the VM. This is more like a cloud infrastructure type of thing. So the right side, you have two VMs. Basically, you can take it like a two tenants running their, basically one shopping cart in one of the WordPress, another one can be another banking application or something. So here you can see the MySQL is listening on the port and SSH port is there for control. So this is the port forwarding is done like the 22 and the 80 is forwarded to 8080 and the 2222 to the host PC. So here we see when you connect to 8080, the Nginx is serving the test page. Basically, its home page kind of thing is served. This is being served from the RISC-V emulator. Then you have a PHP test page. You can see the RISC-64 is written there on the corner. So being served from the RISC-V based emulator. And this is a snapshot of the MySQL database showing the list of databases present there. WordPress is there, VM dashboard is there, several other test databases are there. This is just to show these things are working here. Then the Bodhi site is being served from the web server, which is running that. The WordPress is serving this Bodhi web page, home page actually. So this is the snapshot of that. And the VM dashboard is showing the active VMs running there, basically, which is going to serving the pages and stuff actually.
The way the team approached this is we took this demo for this event, right? That's what we planned in 4 months, how we can assemble. So we approached as a subsystem by subsystem, how do we do this, right? You know, we assembled the QMO with the basic boot and firmware getting loaded, followed by, you know, putting the OS and the kernel getting it up. And then we picked this use case. Obviously, Jim picked this, you know, that'll be nice to show. So then the next subsystem, as Ratina mentioned, is each of these middleware layers of how do we get the virtualized environment as well running in the actual RISC system. So that is another subsystem we worked on, which needed changes in all the layers with actually the virtual machine manager dashboard, which is obviously the graphical interface, which is getting hosted in the RISC system, you know, that is running this, which you're able to show that 3 live systems going on, and which you're able to do 3 web server rendering to the client, right? So again, it's all in emulated, but all the software pieces of it get it running. Our strategy is, you know, as we enter more, we want to completely left shift the software readiness, right? You know, along with our hardware, well before the hardware even, you know, gets the RTL done and code done with the emulated environment, followed by, you know, RTL simulated, followed by, you know, actual, you know, silicon, you know, that comes along. So that's where we are accelerating, you know, how the whole software we can get ready. Our is, you know, upstream as fast as possible and collaborate with all and make it more faster, right? And together, right? You know, and obviously smarter. Yeah.
This is a diagram which is showing how this is assembled in little more deeper way. So basically the blue box is the x86 64 PC, which is running Ubuntu. And the green box is the RISC-V emulator. Basically, this is a main RISC-V system, server system kind of thing. So the second green box is the software which is running basically Linux Ubuntu, this 64 based. So which is running the Nginx SSH, PHP, MySQL, and UART port. Basically the configuration is here, 8-core configuration, and the extensions are listed here. And it's 8 GB memory with serial port and 80 GB storage is given. This is the RISC-V server configuration kind of thing. The port forwarding is shown here, how these ports are configured with 2 core and 2 GB memory. This is more like one tenant is asking for one VM for hosting his page kind of thing. So here also we are running this basic building blocks, inside web server based building blocks, and WordPress is running on top of this actually. And here you see a 2-level port forwarding, and the VNC is connecting, basically the no VNC has forwarding set here to visualize the console in the VM dashboard itself. Basically the as administrator, you can control this VM directly from the web server, basically. Okay, so as a conclusion, we want to touch upon the challenges and whatever we have for the basic thing. So basically, it will be like 50x slower compared to other development. It will be running very slow. So the performance and optimization, basically the power and performance optimization using this model itself is a big topic on its own. How you collect the traces from the QMO and how do you feed it through the power model or performance model, get out the top hitting hotspots and optimize them. This itself is a big challenge in the emulation. So then we need to have the IP models. Basically, everybody will choose different combination of IP. We need the models available for everything in this free silicon. These are all the challenges. So this is where the opportunity lies. Basically, everybody can pick each challenge and basically solve one of these problems, and we can leverage together. Then the porting. Basically, many of the software things, it does not support that cross compilation. Cross compilation, it's taken for granted, like people compile natively. So this is where the challenge lies for us, because basically you have to compile it in the QMO itself. Basically, that means you will compile it at 50x slower speed. That is one big challenge. Then the pre-built libraries, many libraries are available, but the right version, picking and choosing the right version, right combination, that itself is another challenge. And making the several source code, pre-compiled source code available as a pre-built, packaged Docker type of thing will be another challenge here. The differentiating things, basically the power management, security type of things are still evolving. Basically the specs are still being evolved for RISC-V. This is where we all can contribute together to refine the spec in the early phases, and we can make it better. A system, so the tools that, for example, the performance, what I touched upon before, the performance optimization tool itself. I mean, you have plenty of tools, but everything is not fully available. You won't be getting a rich experience. We have to fix all those things. We have to get a wide variety of tools, then integrating everything together. And the system level optimization is another key challenge, because you have to optimize across the layers, basically. That is another challenge. Basically, these are all the areas we can dive together and solve the problems.
Yeah, again, this slide is to show rather than as a challenges, this is what we believe, we cannot come together to solve. And it's evolving fast, and these are all problems already been solved before in other architecture. So it's not unique that the RISC is going to solve. The good news is, the ARM, has went through this, which is going to be helping us to make it more faster. So as I mentioned, industry learned much from ARM-8 enablement. So the required timelines and constraints is, again, as I mentioned, we have to start early with software. Maybe maybe the hardware folks can a little relax, but it's going to be for software folks to come together, start early, and code upstream it. And scope discovery, right? Which is a long tail in the software packages, so which you need to handle it. Always think from deployment, right? As a software, as a system, we need to think from what is my deployment is going to look like, and break down that to the next level, which is always help to realize the customer use case more faster. And then we help in, when I say software community helps in defining the contract for the hardware much more better. And that's where I say software leading from front is very key, for this, I would say a transformation, which is very key, right? From, as Jim talked about, 86 from 2 to 5 to 20. I think the software is going to open the doors for more bigger, okay? So scalable enterprise approach, the standards always works, right? And open source always works. So that's the mantra, and we are going to follow that. And that's how we are going to scale it. Don't do it alone, right? Partner with broader ecosystem. So that's another key. Collaboration on a shared base still allows market differentiation, which is possible. So we do not need to hide behind that. We need a differentiation that always can come from performance and other use case enablement, how fast we can do. But that plenty of opportunity due to the differentiation. From the RISC-V software, evolving much faster than other ecosystems, when we are able to quickly assemble and able to bring up one use case faster in a simulation in couple of months, I think the ecosystem is much faster compared to other. And we expect significant progress during 2023 with Google just endorsed on Android, which we are going to hear the next session, which is big. And we do believe other ecosystem is fastly catching up. Partner and collaborate for acceleration. And it is going to be a shared destiny. It is not going to be a single destiny, right? It is going to be a shared destiny for us to transform the world, and collaboration is the way forward. And also there is a group effort on software, particularly is getting formed under RISC-V International, which is going to bring us much more in a formalized and organized fashion, which is going to happen. Okay, so with that, our socket is implemented. We are in a listen mode. Our interrupt handlers are already alive. You can trigger as a nerds, and we are ready to, and we allocated big memory to listen. So anything you can throw, we are ready to partner. Yeah. Thank you, and we'll open up for Q&A. Yeah.
Say it again in the microphone.
So when is the integration of hardware touching the software, the rubber testing the road, right? So when is that?
Yeah, I think as Jim covered in his roadmap, right? Right now with our partnership, currently we are thinking, the AI roadmap, already couple of generation of hardware with Tenstorrent available. We are already, trying it out with that IP. With that emulation, we want to get our software with the community, obviously, to get it ready by early 2025, and then the core and other IPs as it get ready, maybe mid 2024, and then maybe Jim, you want 24, yeah. Yep, 24. So he put the timeline now.
So you talked about a lot of markets. Which markets you will be focusing first, or like you want to target all the markets in 24, 25?
So we are exploring a couple of customers. Obviously, we are very early enough to disclose the customer information, and we already hinted a little bit of the server segments. And our focus is get the common ingredients and common IPs and common system. Obviously, we are going for a chiplet-based integration, which makes us much more easier as we approach our different segments faster. So you can make your own guess. Quickly we will announce that segment where we are entering. Yeah.
Thank you.
But we'll be targeting all segments as we move forward, but obviously a couple of segments to start with. Yeah.
So I'm curious to know how fast is your QEMU emulator? Yeah, how fast are your simulations to, well, your emulations of the software stack? Because these are big applications.
Slower actually. The question is how fast is the QEMU emulation? That is 50x almost slower. It boots very, very slow.
Hi. So sorry, I'm still compelled to do comparison between the existing ecosystem and the upcoming one, right? So pardon me if you find that not encouraging. But the effort, if I look at from a third person point of view, looks like porting or creating an ecosystem or porting of the software stack for a RISC-V based hardware platform, right? So what do you think is going to bring a differentiation in terms of performance for these products? Is it the hardware platform, or is it the software stack that we are building that will bring a key differentiation in terms of offering better performance with respect to the existing ecosystem?
It starts with everything, right? For example, the performance and power can start from the SoC level, but at the same time, the software also can leverage basically the optimization in the software what we do. That itself can give a better performance in some places. The several things are not ported. For example, if you take a math library, it works in a pure C-based mode here, so which is not optimized for RISC-V. So there itself, if you do a hand-coded, hand-modified optimization there, you will leverage a lot of performance. So such things can be differentiating factors. At the same time, you will still contribute to the open community, because that is what Android, Linux was doing over the period of time. So they start exploring something, they make it mature, and then they will use it, and then they will deliver back to the community. That's how the differentiation.
One of the key opportunities we see, right, is the open hardware architecture, which allows the ISA to be defined faster here. Because if you look at I'm purely talking from the software and then system, which allowed us software to catch up with the hardware defined first, right?
Okay.
So with this ISA, with the team working closely between hardware and software, that's why I stress the hardware contract, which is much easier to define now and influence the ISA inside, and then how we expose that ISA much more friendly to the software is something we can do better in the RISC ecosystem compared to the previous ecosystem, which was much more closed and took multiple years, to define even one single instruction. Right?
Hi, Raghu. So the question that I have is that, I mean, if you look at the market, Amazon has brought its own ARM-based processor, and Intel also claims that, okay, there's so many billion lines of code that's been written on x86. And now the other question I also have is that, okay, let's say you're working closely with Tenstorrent, but tomorrow some other company comes up with an equivalent chip or as powerful as Tenstorrent. How is your system in a position to handle both the companies? Let's say there's something like an AMD Intel kind of a thing for in RISC-V. And next, in the sense, how are you differentiating yourself? Like, how do you get the market of Amazon, who's trying to say that, okay, we want to build our own processors, and instead of what makes you different, so that they take your processor or your system and integrate it with them?
Yeah, I'll take the second question first. The customers are pretty open, right? They were locked with the 86, but with ARM coming, you would have seen already customers are pretty open to change this, movement from one architecture-based deployment to other-based architecture. I don't think it is hard with customer moving. I think it is about how easy we can make them to move is where the software and hardware, how it is comes, and deployment thinking. That's what I was mentioned. If we solve that problem faster, I think the bottleneck is not customer adopting our systems or solutions, right? If we make it harder for them to achieve that, then it's easy. But that the mind break of moving from one architecture to other architecture is already broken now, right? They want a more open, systems and solution from multiple vendors, obvious, because as a customer, I like multiple solutions to come with me, right? That creates a healthy solution that benefits customer both from cost and time and flexibility, right? So with respect to the second, when I say, I'm stressing the fact that Tenstorrent Bodhi, but that's where we started, and I'm keep stressing the open hardware interface contract, which is be open, right? And Tenstorrent is leading, from the front to be working openly, and that is the reason Jim's vision and others' vision is to create a group of companies with this mindset of contributing back to the community and how we create this system more faster openly, so that any interface, as we talked about standard and interface, we keep it open so that everybody can contribute and make it faster through open hardware interface as well as open software. And then the question is, when everybody follows that, the migration is easy. How many questions you can take more? Okay. So good, we can cover that more detail there. Yeah.
And another
Yeah. So we do see, as I told, one of the segment is the infotainment and how we see moving forward the domain controller in the autonomous driving, how closely those two has to interact. When we say Android, we are not looking only from the UI side of it. How the system interacts with the other system is important. That's why we're saying connected services, which we see is going to be more between the services of the different worlds of the OS is very important as well, right? Yeah.
Thank you.
Yeah, so we did a market analysis statistics actually. Maybe we had put in the backup. So basically the top used server is the Nginx web server, and the top used content management system is the WordPress. That's what we saw in the statistics of 2023 January timeframe. So that is what we took as a basic reference, because once we get it, we get a bigger reach basically. That is the main reason for that. Okay, basically this is emulated, so you don't get the actual numbers here. That's what I had put as a challenge, right? The actual
of the industrial standard emulators already, or still waiting for the customer to provide? How is the model you are planning? Are you planning to own your own emulators, or you are expecting the customer to provide the infra?
In the emulators?
Hardware emulators.
Okay, it depends actually. It's like so we have to do something on our own in the emulator. Whatever we are doing together with Tenstorrent, that we will have to add the support here. It's like a collaboration with Tenstorrent kind of thing. For the other things, the other end, it's a collaboration kind of thing actually. Yeah. So it's not like we own everything.
Okay.
So back to your Android integration that you said, are you also opening up the Linux kernel as well? Because we generally in infotainment and ADAS applications, we would like to run some of the code on bare C++ on Linux rather than being tied on to Android Vision APIs. So how are you kind of architecting that?
Yeah. So that's technically possible, right? Basically, that problem is already solved for the other architectures. Basically, we are trying to replicate whatever is already solved. So that way, so you can have the containered kind of isolation. Basically, you can have.
Please speak a bit louder. Yeah.
So basically, this problem is not new, right? Basically, whatever you want to run in a native mode,
Right.
it's already solved problem for the Android purpose actually. So basically, you can run an Android along. I mean, you can have a side by side. You can have another container which is running this kind of dedicated content, or if you want it to be more trusted, you can have a secure OS hosting its own services type of thing. So basically, you can have different architectures based on the requirement, what the problem we are going to solve. We will freeze something and we will move forward here.
Sure. We would like to get some details on when your ADAS board is going to be out, or the chip, and any manufacturer which will give us the board. We can take it offline. I'm Shivendra, CTO for ChipLogic.
Yeah, thank you again. It's excellent questions. I think we are really pumped, to see this kind of active participation and grilling questions. This is what we expected, to open it up and connect. And I think we are meeting the purpose of this, at least for this session and the event. And we are available, as I mentioned, to listen in and collaborate, to get your ideas, thoughts, and as we propel forward. In the interest of time, again, thank you again for the wonderful opportunity. Being a small company, getting this stage and come front. Thank you, Tenstorrent team, to put us front. Thank you. Thanks a lot.
Thank you, Raghu. Thank you, Bodhi team. Next up, we have Lars Bergstrom, Director of Engineering at Google, who will be joining us remotely. He has sent us a video that we'll play here. So he'll be talking about support for RISC-V in the Android open source project. Can we play the video?
Talk with all of you about the Android operating system, the Android open source project, and our progress. Supporting the RISC-V architecture since we first announced it last December. I'll also close with some updates on some of the really interesting things that we think we'll see. So today, I'm really excited to get to talk with all of you about the Android operating system, the Android open source project, and our progress with supporting the RISC-V architecture since we first announced it last December.
Can you guys hear in the back?
I'll also close with some updates on some of
Raise
the
your hand if
really
you can hear in the
interesting
back.
things that we think we'll see in the near future.
Oh, okay.
But before we get started, some terminology. So Android is the open source operating system for mobile devices that many of you are probably already very familiar with. The Android open source project, on the other hand, is the corresponding open source project led by Google. So this project provides everything that you're going to need in order to port the Android operating system to new hardware and ensure its compatibility. Now, however, it does not include the Google Suite of Applications or the Play Store. Now, AOSP is freely available to anyone who would like a capable operating system that runs on many form factors of electronic devices. It provides access to a wide range of development tools and libraries to easily build or port applications to these devices. Many vendors in the ecosystem produce such devices as e-readers, virtual reality headsets, as well as a whole lot of things in other form factors. And really, this diversity of ability to support different form factors has led many vendors to join and make use of the Android open source project. So while it's most known for running on phones, Android was really originally designed to run on cameras. I mentioned e-readers and virtual reality machines, but Android is also on tablets, watches, televisions, and automobiles. It also has Internet of Things integration so that Android can communicate with everything from your lights and your sound system to your fridge. And, of course, you can actually get a camera today. So the question is, So how does all of this work? How do we have one set of sources that enables a broad and diverse developer ecosystem? And really, AOSP is the key to that. It is the common set of sources that are used by all of the players in the ecosystem. So when you add features, or in the case of all of us here working on RISC-V, platform support to AOSP, you not only enable the silicon partners across the top of this slide to develop new applications, but you also enable developers down the side of this slide to port their applications and build new ones without requiring custom tools. So that set of sources, APIs, compilers, and tools that are used to build the operating system sits on top of the hardware is delivered to all of the devices. Those same sources build emulated environments and developer tooling that will be given to developers to build their applications. And so really, what you want to take away from this is that AOSP is the common element, ensuring that we can have a diverse set of players in both the developer ecosystem who are building applications, as well as in the hardware and vendor ecosystem who are building and shipping new devices. And they can interoperate without having to necessarily directly coordinate with one another, because the point of coordination is the Android open source project. And this isn't unique to RISC-V, right? This is exactly how everything works for all of the different architectures that AOSP supports, whether it's x86, ARM32, ARM64. And so RISC-V 64-bit is just the newest in a long line of architectures that have been supported by the Android open source platform. So for a bit of history on it, I think all of us have been watching RISC-V eagerly since at least 2018. But it was really in 2021 where the developers at Alibaba's T-Head group and all of their partners were able to get the first build of Android 10 running on real RISC-V hardware. And what's really great about it is not only did their team do this port, but they made their source code available. They even updated it to Android 12 and opened up all of their patches for upstreaming into the Android open source project. And so you'll notice in this talk that this is kind of a theme around all of the software work required in order to make RISC-V successful on Android, that these contributions to a broad variety of open source projects, but including AOSP, is necessary in order to have full support to enable those developers to bring their applications to all of the new devices that we're seeing people begin to both think about and bring to market in the RISC-V space. So in October of 2022, we began directly landing those patches in support for RISC-V. And much of it was built off of open source and third-party contributions, or was based on those contributions in order to build something that could integrate well with all of the different parts of the Android open source project and mesh well with all of the different platforms that we support. But of course, as we know with open source code, you can't just write it once and expect it to continue to land. So both AOSP and many of the other projects in the ecosystem have thousands of commits per year and are very fast moving. It's hard to keep things working on platforms that have millions or billions of users, much less one that's still emerging. So one of the first things that we did was establish a continuous builder so that we could treat our RISC-V builds as a tier 1 supported platform against the main branch of Android. Now, we were really cautious when we took this step because it's much easier to add new platforms than it is to remove them. Even today, as we add the new RISC-V support, we are finding many places where there's leftover code from previous architectures that we end up cleaning up. And I want to call out a second theme here, that of only having 64-bit support. While we recognize that 32-bit RISC-V is incredibly useful in a broad set of scenarios. For an application core on a modern computing device, we really do want to set the minimum bar at 64-bit. So whether it's avoiding time T wrapping around in 2038, a time when many of these devices, soon to be released, may still be running, or just access to all the modern security features that take use of extra tag bits in the pointer, 64-bit pointers and integers are a baseline going forward for a modern operating system like Android. So even in 2022, during and after I gave my update at the RISC-V International Summit December, there was significant progress heading into the new year. So we got emulation and boot support, which enabled us to do additional development and testing on host platforms. What this basically did, it didn't have graphics yet, but it had the ability to connect in from the shell and begin running additional benchmarks and making sure that all of the native code, all of the C and C++ and Rust services were working well. We also got much more engaged coming out of the summit at the RISC-V Special Interest Group. We brought in many more contributors from across the industry to work on all of the known open issues and really to help us to pull together and centralize all of the gaps or opportunities for additional support. And it's not just that support and that set of features that we needed in the open source software. We needed to engage on making sure that we have a great ABI. One of the hallmarks of Android is that our application developers can target some very early devices and their code will run there. And it will also run on much newer devices, up to 7 or even 10 years of range between the release times of these devices. And we really want to make sure that as RISC-V evolves and as we adopt these new features on Android, that developers are able to target the broadest parts of the ecosystem, but also take advantage of new features. So we can't have destabilizing ABI changes where we say, oh, well, you can either build your application to target all of the devices in the ecosystem or just some of the new emerging devices. From all of our experience with Android, we know that that's not how our developers want to work. The magic of Android development is being able to light up on these new devices. We also identified some really key gaps that we want to help address, and so we've been engaging upstream in the community with those. Whether it's atomics or instruction data consistency, basically being able to support the way that Android works really requires some special instructions in the CPU in order to do that well. Android is basically a very large operating system made of many Java language processes, all communicating with one another and calling into and out of native code. And so these interactions between the native code and the managed code, the runtime, the just-in-time compiler, making sure that we can have really great instruction sequences and lightweight atomics that allow us to dynamically generate code and jump in and execute it is really important to make sure that not only do RISC-V devices run Android, but that they run it really well. And all of this has really brought me confidence coming to today that we'll be able to not only have AOSP run, but like I said, have it run really well. And of course, we've been engaging a lot on the security and virtualization side. Coming back to what I mentioned about modern devices and modern requirements around 64-bit, today in 2023, we also have a very intense security and privacy burden that requires that our hardware make sure that it's keeping our users' data safe, that it's isolating computations from one another, because there are a lot of bad actors and mobile devices are one of their top targets. So that was 2022. Coming into 2023, we have gotten graphics working. So basically now in the emulator, we also have local graphics support as well as the ART Java language interpreter running. And what this does is it allows us to start running actual Android applications. So as you could see from that video, that was us launching RISC-V inside of QEMU and taking advantage of the new graphics capabilities in order to see it running some applications. This not only allows us to to do some local development and testing, but it also allows us to do continuous integration and automated testing. Having support for that was a real blocker to being able to run the full test suites that ensure that that the platform that we are building and the devices we are running it on are correctly able to implement the Android APIs in the Android open source project, so that when developers port their programs over from any other platform that they were supporting, that things all run the way that they were expecting on top of RISC-V on AOSP. So that's not just demo code, is what's really nice here. All of this code is actually landed in upstream master, is being tested, and so this is all production quality code at this point. But again, one of our real concerns here was making sure that we have a good initial baseline. That is, that the set of features that are provided by the set of RISC-V specifications that we assume are there allow us to implement the Android open source project really well. So in previous experiences on Android, we've had software emulated floating point, we've lacked SIMD support, and it's taken us 7 or more years to move and get adoption from our developer community. And that's a mistake we really don't want to repeat with RISC-V, so we want to make sure that we have the vector extensions enabled all throughout the stack, and that we continue to pick up and extend usage of all of the other great specifications that are landing right now. Of course, that also means that it's going to be important to invest in loader and software support for hardware feature detection. So not only is there a great baseline, but one of the great innovations in RISC-V is that there are both a lot of new specifications coming out, as well as custom vendor extensions. And so we know that our silicon partners are going to want to innovate very quickly. They're going to want to create new features that can accelerate AI or help with camera and media workloads. And we want to make sure that they can take advantage of those in their board support packages. And for the things that are standards track and land in specifications, we want to make sure that our developers are easily able to tool and pick up and use those new features. And so all of that, all of this evaluation, the tooling support, the matrix of the interactions of these features with one another within the software, that's pretty challenging. And that's even before we talk about just how quickly moving everything is in the RISC-V space. So that was pretty high level. Let's get a little bit more concrete about just some of what goes into the addition of a new extension and its usage in AOSP. So we'll use the RISC-V vector extension as an example. Now, for some quick background, the vector extension allows a program to ask the processor to perform operations such as multiplication and addition across a variable number of elements all at the same time. So rather than writing scalar operations that work on single elements, one integer plus one integer times one integer, or SIMD instructions that are a single instruction working on multiple but a fixed number of elements at a time, say 2 or 4 or 8 or 16, vector operations do not require the software developer to determine ahead of time the bin size or sort of the breakdown of their operations over a lot of data. Instead, they leave that to the chip designer, who can decide in their own vector unit how to break up and process that data in order to perform the operations that were selected. So this isn't just some esoteric feature. Programs need to perform the same operation over variable lengths of data a lot. Not just sort of the obvious cases around high performance computing, but these kinds of algorithms are at the heart of modern AI and ML. They arise in web browsers and all over our common library functions that clear, sort data in memory, perform cryptographic operations, etc. So in 2023, many platform features, applications, and even our benchmarks just expect the compiler to both be able to directly make vector calls, as well as sometimes automatically turn normal sequential code into vectorized operations. So when a new specification as big as this comes along, we can't just add an inline assembly block to some code and count on everything to work all the way down the stack. There are many pieces here, which I've called out in this slide. The Linux kernel needs support for the feature, it needs to expose the registers, and it needs to integrate well with all the other kernel features, syscalls and the rest. In order to be able to test the feature, the virtual machine emulator needs to be able to emulate the features, and it needs to be able to do them efficiently so that we can test out the code. Our compilers, which on Android means the LLVM toolchain, need to be able to directly emit the instruction. And then many libraries have hand-rolled operations to support this where it all needs to work. And even beyond the libraries, sometimes we have tools, whether it's the linker or the loader, that may need fixes in order to support and understand these new instructions. So as a community, not only do we need to land this work, but we continuously have to keep it working. It's easy for some of the exciting and rapid progress here to cause breakage. For example, as of this morning, there were some regressions in code generation around a new and super useful bit manipulation extension that we use, and we'll need to help work to get that fixed upstream before we can update our compilers and pick up any new features that we want that are associated with automatic vectorization. It's a really complicated stack, but one of the great things is that as we see more participation, we see more testing and more stability, which is just great for the entire RISC-V ecosystem, even beyond Android. So in 2023, we want to go from just working, like I mentioned and you saw in the video, to working reliably and quickly. The top priority for us over the next quarter is optimizing our JIT compiler and building out a fast interpreter. We need the Java code to run fast and well. There are many tens of services that are running in the background, all written and running on top of the Android runtime at the same time that any application is running. We also want to continue our work with the community of developers and vendors to ensure there's a solid forward-looking baseline for AOSP. Of course, any vendor is welcome to customize and ship AOSP with either additional or removed extensions. But we're really trying to find a great initial set together, make it work really well, and keep it working well. There's a lot of progress as well in the security, power, debugging, and tracing specifications, as well as some really exciting work around continuing to reduce code size. Reduced code size has some great benefits on the limited storage and memory of client and edge devices. No matter how much memory or storage we add to our devices, our users always wish they had more. And so finding out which of those are going to be useful, what's their impact going to be on real world code, and how implementable are those features by all of you in our vendor community working on new hardware is really one of the big questions for us for 2023. We're also seeing some really great progress, including from many vendors at this event, in bringing more advanced application processor quality RISC-V designs to the market. And so we want to help them get AOSP running on their hardware and hopefully get help and feedback from all of you as well on the features we're implementing in AOSP, the specifications that we're counting on, and how it's all working together. Now, all the work that I've described here will continue to be published in the open, and many of the discussions as well are happening in public, either at RISC-V International or in the Android AOSP RISC-V specific GitHub's issues repository. I would absolutely welcome any feedback and conversations that all of you have there. And that's really what I'd like to close with. There are many ways to get involved here, from contributing code to documentation to specification work to testing. And the best way to find these opportunities is to join the special interest group on Android hosted at RISC-V International. We have an active discussion list as well as regular calls that are open to any RISC-V International member to attend. And that group is also where we share a lot of updates on progress and, well, as bring up new gaps that we've identified to try and find out whether we can solve it within the Android special interest group or whether there's another working group at RISC-V International that will help us. So In close, I look forward to continuing to collaborate both on the RISC-V standard as well as on many open source projects throughout the Android ecosystem with all of you. And I can't wait to see the hardware you build, the products that your ecosystem brings to market, and the incredible things that developers build on top of them. Thank you again for all of your support.
Thank you, everyone. Now we'll break here for lunch, and we'll be back at 1 p.m. for the next set of talks. Thank you. You can have the lunch in the lobby, and it's arranged for you downstairs. Thank you.